Hi everyone, this is Prof. K speaking, and today we're going to be talking about reaction stoichiometry, which is in chapter 7.3. Our learning objectives for today are to be able to explain the concept of stoichiometry as it pertains to chemical reactions, to use balanced chemical equations to derive stoichiometric factors, which relate the amounts of reactants and products to each other, and also to be able to perform some stoichiometric calculations involving variables such as mass, moles, solution molarity, and even potentially particles. So to start, what is stoichiometry? So stoichiometry is defined as a quantitative description of the relationships between the amount of substances consumed and produced by the reaction. So when we balance a chemical reaction, such as the photosynthesis reaction, stoichiometry is us specifying that you need 6 CO2 and 6 H2O to produce 1 C6H12O6. So it's a mathematical representation, which is what quantitative description means. It has these sort of sixes and ones and potentially other numbers that can tell us how much of a reactant or product do we need to do some reaction. And so some way that I like to think about this, and that a lot of people like to think about stoichiometry is a reaction recipe. So it tells us, just like if we were trying to make baklava, that in order to make 1 pan of baklava, I know I need to put in a box of phyllo dough, a pound of pistachios, 2.5 sticks of butter, and so on. So I have all these ingredients that I need in specific amounts. And stoichiometry is us thinking about the specific amounts. So it's how much I need of something in order to produce something else. Or how much phyllo dough do I need for a certain amount of cinnamon? What is the combination in a quantitative sense of the ingredients that make what I want to make? So if I wanted to, I could write this recipe in terms of some ratios. So if I have a pound of pistachios, then in order to make baklava, I'm also going to need a cup of sugar. If I want instead, if I have a teaspoon of cinnamon, then I know I need half a cup of honey. And if I want to make the pan of baklava, then I'm going to need 1 pound of pistachios. So these are ratios of our ingredients or our product to each other. So a ratio is a comparison of 2 amounts. And so here our ratios are based on the amounts of ingredients we need in this recipe. And so we can do the same process for that photosynthesis reaction, which is if I have 6 CO2 molecules, I'm going to need 6 H2O molecules. And I can write this as a 1 mole of CO2 per 1 mole of H2O. And if I actually want to make a glucose, then I'll need to be able to have 6 moles or 6 molecules of CO2, depending on if we want to make a mole or a molecule of glucose, that I have to put in. And so these ratios of individual chemical species are what we call stoichiometric factors, which is how we connect the idea of 1 mole of an ingredient or a product to the amounts of the other materials we need or that we can produce. And we get these directly from the coefficients in balanced chemical equations, which is why it's really useful to be able to balance chemical equations. Because if I had the recipe for baklava and I knew all the ingredients, but I don't know how much I need to have of each, the chance of me making a nice pan of baklava is pretty low. And so the chance of me doing the chemistry I want to do is going to be much lower if I can't describe how much of each compound I need, and if I can't start to do some calculation based on how much of each compound I need. And so stoichiometric factors allow us to do all sorts of calculations. And this is a big figure with a lot of connections. I'm going to walk us through some sample calculations as we navigate this chart to help you get used to what it means. But ultimately, it shows you the ways that you can connect different values to each other through some dimensional analysis based on what we need to go from one unit to the other. So if we start in the center of this and we talk about stoichiometric factors like we have been, I would like to know how much glucose can 1 mole of carbon dioxide produce? So if I look at this equation, I'm asking if I put in 1 mole of carbon dioxide, how much glucose can I get out? And so to do this calculation, I do some dimensional analysis where I say 1 mole of CO2 is my input, and for every 6 moles of CO2, I produce 1 mole of C6H12O6, or glucose. And so this is a stoichiometric factor that I pulled directly from the coefficients in this equation. And there's sort of an implied 1 if we don't have a number. And what that tells me is that if I have 1 mole of CO2, I can produce 1/6 of a mole of glucose. So if I only had 1 molecule of CO2, I couldn't produce glucose because I need 6 molecules to get 1 glucose out. And so this is an example of moving in the center of the chart. I can go from moles of one of my compounds to moles of another via this stoichiometric factor. So I multiply moles of A by the stoichiometric factor and I get moles of B. And then if I expand the chart a little bit, I can also go from a volume of a solution to these moles and then across this flow diagram and calculate a new volume. So if I consider the question I have here, which is if I have 10 milliliters of 0.6 molar HCl and excess calcium hydroxide, how many moles of salt will I produce? And so I've balanced the chemical reaction for you, though potentially on a problem you could be asked to balance it before we moved into it. And then I can start to do dimensional analysis. So I can say that if I start with 10 milliliters of solution and I want to be able to multiply it by molarity, so I start here, 1, I want to multiply by molarity, and in order to do that, I have to convert from milliliters to liters, and then I can multiply by the molarity I've given, and I go from a volume to a moles of HCl, and then I can use the stoichiometric factor. So at here, I'm at 2, and then I can, so this is step 2, I multiply by the stoichiometric factor, and I get 1 mole of calcium chloride for every 2 moles of HCl, which I derive from this balanced chemical equation. And that tells me the moles of salt, 3, where I want to go. So I can use multiplication and dimensional analysis to move across this chart and calculate quantities that I'm interested in. And these quantities can get even more complicated. So if we know the molar mass of compounds, then we can move around this chart and also predict the masses we need of different compounds. So for example, if 5 grams of calcium chloride is produced by the reaction of excess HCl and calcium hydroxide, what mass of calcium hydroxide would we have had to have added? So I once again start with what I'm given, which is the 5 grams of calcium chloride. And so potentially I'm here 1, and I multiply it by molar mass. So I go here next. I multiply it by molar mass using dimensional analysis so that my grams cancel. And then I want to cross over. So my goal target over here, 4, is the mass of B. I want to calculate the mass of calcium hydroxide. So in order to do that, I have to cross the stoichiometric, so this is step 2. I have to multiply it by the stoichiometric factor, and that will give me moles of calcium hydroxide, which I then multiply by the molar mass using dimensional analysis, and out comes my grams of calcium hydroxide. So I can travel through this figure to do calculations I'm interested in. And so the stoichiometric factor is really important because it helps us connect the properties of one molecule to the properties of another and allows us to do specific calculations about how much we need or how much we might have used or how much was in the solution originally. So we've already done some sample problems in the course using stoichiometric factors, but we're officially labeling them now and talking about them specifically as it helps us navigate this diagram. And so the bottom part of this diagram is to also potentially be able to relate the moles that we have here to number of particles or molecules or atoms using Avogadro's number. So if on the first one, I had instead asked how many glucose molecules can 1.0 mole of carbon dioxide produce, I then still start with moles of carbon dioxide. So if I'm here, I start with moles of carbon dioxide. I multiply by my stoichiometric factor, and it gives me the moles of glucose that I have. And then I can use Avogadro's number to see how many molecules are there per mole of glucose that I have, which brings me down to my goal over here, which is the number of particles. And so even if I gave you a number of particles, you can traverse this figure and use it to calculate a volume if you have concentration, or a mass if you have molar masses. So you can sort of expand out across this table using these multiplications and dimensional analysis to calculate a lot of properties about chemical reactions if we know the balanced equation. So knowing how to balance equations and what that tells us about the stoichiometry or the relative ratio of these different reactants or products helps us move around this plot and is going to be the primary focus of a lot of the activities that we do, is practicing moving around here and doing calculations based on the stoichiometry present in the chemical reactions.